Yes, one more calculation. By now, you should be familiar with the setup. You should be familiar with the terminology. What we want to do here is calculate the percent ionization of a weak acid. We are given the Ka, and sitting below is the ice table. You should also be familiar with how we set up the X's. So how does this one work? Well, remember, K is still products over reactants. What we have is 1.8 times 10 to the minus 5. That is our K. We have X squared over 0.10 minus X. Because there is a difference, 10 to the minus 5 versus 0.10, we can ignore that X, and we come up with a value of X equal to 1.34 times 10 to the minus 3 molar. Again, going a little bit quicker because we spent a lot of time on parts 1 and 2. What we really want to do is find this percent ionization. And to do that, we take the amount of H plus that we just found, 1.34 times 10 to the minus 3 molar. That is the value here. We know that's also pH, but this time we're doing percent ionization. We divide it by 0.10 and we multiply by 100. That gives us the number 1.34%. Why do we do this calculation? Well, it's a good example. You have vinegar, which is acetic acid. That's what we're talking about. For every 1,000 molecules, there are only 13 H pluses and 13 acetate ions. There are 987 unionized acetic acid molecules. So if I were to draw an arrow as to which side the equilibrium would lie on, it would look like that. And equilibrium would lie on the left. It would lie with the molecules. Like, that's a favorite midterm question, so I just want to toss that in. What's left in this section? It's more factual than anything else. Polyprotic acids, they have more than one ionizable proton, and you can see they are bolded for sulfuric, for phosphoric, and for citric acid. Ionization, though, is stepwise. You take one H plus off at a time. All the equilibrium exists simultaneously. We only introduce it here. It is covered in more depth at a higher level course. But the things we want to point out, as you go through the ionizations, and I typed them all out before I came to present this, you can see that the Ka is going to decrease, and it's a huge decrease, 10 to the 4th to 10 to the 6th. It's much harder to remove an H plus from an anion, so it doesn't want to give it up. Please know that if you're headed into a STEM or a field in medicine, you do need to be able to understand and write these equations. All we've done is taken off one hydrogen at a time. Takes practice. There are all kind of get started right here. Here is the 3 of Kas. Now, since we are online, to ask about polyprotics, but let us just equations, and what if they were, say, calculate all the species present in 3 molar phosphoric acid? So what we would do is there is a general rule, okay? When K1 is much, much greater than K2, the concentration of the anion of the second step equals K2. Let's show you what that means, okay? Here is how we would normally write it out. I simply did not make an ice table. I'm hoping that you're at that point now where you know that this is the equilibrium line of the ice table. Here is the K for this process. Here is the K expression. Here is the setup of the math. And there is our value, 0.19 molar. So if I look at what are my concentrations, what is my remaining concentration of phosphoric acid? Initially, it was 3. I subtract the amount that I just calculated. It tells me the amount left of 2.8 molar. What are my concentrations of H plus and the anion of H2PO4 minus? They are 0.19 molar. What is my percent dissociation? Only 3.8%. So when I did my calculation, it was okay to ignore X. That's the first dissociation, the one with the K1. Think of what the sentence meant. You probably couldn't figure it out, but let's show what. I do not know the kind of question that there is now. In the second calculation, this again would be my E line in the table. Here is my K2. There is my K expression. Here it is substituting in the value. We are going to assume the X in both 0.19 plus X and 0.19 minus X can be ignored. When we do the math, what we come up with is X is equal to 6.2 times 10 to the minus 8th. So for the most part in a course like Chemistry 1220, you can assume that the K2 is going to be equal to the concentration of the dianion. Again, don't know how far they're going in our class this semester with the common exam online, but if you're going into pharmacy, medicine, they're going to go into this in more depth. So again, the general rule, especially, well, it's polyprotics, if K1 is much, much greater than K2, here we had a 10 to the minus 3, here we had a 10 to the minus 8th, we will find that the anion of the second step, which would be the one that has the minus 2 sign, it is going to be equal to the K2. And again, in a higher level course, more time we spent. We can also go and do the third step calculation. And again, in the old days, we did all of this math. We did not sacrifice anything. This is our K3 for this third step. This is our equilibrium line. This is the K expression. And here we set up the math. And once again, we are going to ignore X and come up with an extremely small concentration for our trianion. Summarizing that all, let's put it here. We have our weak acid, we have our strong acid. Both of these are polyprotic acids. For our weak acid, again, we have these different values of K. We go with the first H plus calculation, and that would tell us what is the number of acid molecules in solution as we work through all the math. Very few H3PO4 versus a strong acid. H2SO4, you know, is strong. The K1 is very, very large. We assume all of it dissociates, but then we would have additional molecules of the SO4 minus that are in solution. I'm not going to go into more depth. I know they will do that in another course. How are we wrapping this section up? Well, polyprotic acids are found, if you look on food labels, you might see some citric acid. Carbonic acid is what's formed when carbon dioxide dissolves in water. They all have specific Ks. They all have formulas. This just lists them all. I do not know how much depth we're going into this term, but in the old days, we went into an extreme amount of depth because, again, it's teaching you about the behavior of polyprotic weak acids. What do these things look like? I think that's an important thing. Phosphoric acid, you've seen H3PO4 before. You know it is a weak acid. This is its actual structure, and it can lose all three of these hydrogens. How about something like citric acid? That's an additive in food. This is what it looks like. These are the hydrogens that can be lost. So, wrapping up this section, this was huge. Weak acids, a ton of calculations. Maybe they're swimming in your head. We have percent ionization, we have pH, we have equilibrium concentration, we have Kas. We have different methods we employ. Sometimes, well, always, we will use an ice table. Sometimes we have enough information that we don't have to use X's, but keep in mind that the equilibrium concentration of H plus is the same thing as saying pH. Keep in mind that the equilibrium concentration of A minus, the anion, will be equal to the equilibrium concentration of the H plus. All of that is for monoprotic weak acids. We just did a tiny bit about the polyprotic acids. I did phosphoric acid because that's an important one in many, many biological systems. So with a polyprotic, all the equilibrium exists simultaneously. The concentration of the second anion, not the first but the second, tends to equal the value of K. Lots to digest is a good way to put it.